A father pulls his daughter on a sled using a rope over level ground, and the rope makes an angle theta with a horizontal, shown in the figure. The total mass of the sled and the girl is m, and the coefficient of static friction is mu k. And this problem is asking you to express all your answers in terms of those three things, the theta, the m, and the mu k, and any fundamental constants. So the first part is, on the dots, you want to draw and label all the forces, not the components, that act on the system. So we have gravity, the gravitational force, Fg, going straight down. It's on level ground, so the normal force, the Fn, is going straight up. The frictional force acts against the motion, so that's the Fr. And then the father is pulling up at an angle on a rope, so it's tension, which is Ft. And you have to label what each of these forces represent. So the Fg, the Fn, the Fr, and the Ft. So the first one is the gravitational force of the Earth on, and we're just going to call it, it's because we're looking at the sled and the girl as a whole system, we'll say the gravitational force of Earth on the system. The next one is the normal force of the ground on the system. The frictional force, since the sled is moving, it's kinetic frictional force. Of the ground on the system. And the last one is the tension force of the rope on the system. So in part B, you want to calculate the force that the father exerts to keep the sled moving at a constant speed. So the first thing we want to do is to break the forces into components, but remember, don't do it on the original free body diagram. So you're going to want to draw a new free body diagram. So I'll just draw a second one down here. And in this case, we don't want to rotate the axes because three of the forces, the normal force, the gravitational force, and the force of friction, already line up along those axes. So we'll just leave the Fn, the Fg, and the Fr, but then the tension force, will break that into an x component and a y component. And since the angle is taken with respect to the x-axis, that means the horizontal component will be Ft cosine of theta, and the vertical component will be Ft sine of theta. So now that we've done that and broken everything into components, we can do the sum of the forces. So we'll start with, let's just say the sum of the forces in the x direction is equal to, now the sled is moving at a constant speed, it says that specifically in the problem. The father pulls his daughter, and it says that in part B, it says calculate the force the father exerts to keep the sled moving at a constant speed. So since the sled is moving at a constant speed, it's not accelerating, so the sum of the forces is going to equal to 0. And remember, whenever the sum of the forces is equal to 0, that just means you can set the ones on the right equal to the ones on the left. So we can just say that Ft cosine of theta is equal to Fr. So that means that Ft cosine of theta There's no formula to plug in for the Ft, that's tension, but there is a formula to plug in for the force of friction, which is mu k times the normal force, the Fn. That's as far as we can go right now, because we don't know what the normal force is. And the way to find the normal force is, since that's in the y direction, is you have to do the sum of the forces in the y direction. And that's equal to 0, since the sled is not even moving in the y direction, so there's no acceleration in that direction. So when the sum of the forces is equal to 0 in the y direction, you just set the upward forces equal to the downward forces. We have two upward forces, the Fn and the Ft sine theta, and that's going to equal to the one downward force, the Fg. So Fn plus Ft sine of theta equals Fg. Now plug in the formulas. So Fn plus Ft sine theta is equal to, the only formula you can plug in is gravity, is mass times, is the gravitational force, is mg. And we can rearrange this equation to get the Fn by itself, because then we could take that formula for Fn and just plug it in for the Fn over here. So Fn is equal to, we'll leave the mg on that side, and then we're just going to bring this term to the other side of the equation. So it'll be minus Ft times the sine of theta. And now that whole equation for Fn we can plug in right here. So what we're left with is Ft cosine of theta equals mu k, and in place of that Fn, I'm going to write this equation, mg minus Ft times the sine of theta. So in this equation, we don't know Ft, that's what we're asked to find. We do know theta, that's one of the constants we can use. We do know mu k, we know m, g is a fundamental constant, and there's the Ft again that we're looking for, and again we know theta. So this equation, this whole equation, only has one unknown in it, which is the Ft, but that shows up in two places. So we need to get that one thing that we're looking for over on one side of the equation. So the first thing I'm going to do is just distribute. Ft cosine theta is equal to mu k mg minus, and we're going to distribute the mu k on the second term also. So mu k Ft sine of theta. Now I want to get all the terms with an Ft over on one side of the equation together. So I'm going to bring this whole term over to that side of the equation. So that leaves me with Ft cosine of theta plus mu k Ft sine of theta equals mu k mg. Now look at the Ft on one side of the equation, one here and one here. To solve for the Ft, I'm going to have to factor it out. So Ft times, in parentheses, the cosine of theta plus mu k times the sine of theta equals, just leave the other side how it is, mu k mg. And now your final step to get the Ft by itself is to divide both sides by this whole entire thing in parentheses. So the final answer is, and I'm going to actually bring this up over to here, is Ft is equal to mu k mg divided by cosine of theta plus mu k times the sine of theta. Second part of the problem says, upon reaching a snowy incline, the father gets behind the sled and pushes horizontally to to move it up the incline. So now the angle of the incline is theta, as shown in the figure, and the coefficient of friction is still mu k, and we're still going to assume the mass of the sled and the girl is m. So on this new dot, draw and label the forces. So most of them are going to be the same, just pointing in different directions. The only one that does not change at all and hold on because I'm screwing this up. So there's the dot. Okay, the only one that does not change at all is the gravitational force, still going straight downward. This time, the normal force is perpendicular to the surface, so that's your Fn, and your frictional force is parallel to the surface, so those are both tilted. And then your pushing force, no longer tension, it's just a pushing force, is the Fp, which is going horizontal. So, to label these forces and identify them, the Fg, the Fn, and the Fr all have the exact same description as before. So I'm not even going to bother putting those down. I'm just going to change the Fp, because that is now the pushing force of the father on the system. So the way this problem is set up, since the sled is still moving at a constant speed, if you look at that's what it says in part D, that means there's no acceleration. So there's 4 forces on here. 2 of the forces would line up if you rotated the axes, and 2 of the forces would line up if you did not rotate the axes. So this problem is kind of 50-50 as to if it's beneficial to rotate the axes or not. It's not going to really benefit you one way or the other. So normally what I do is for problems on inclines, I just always tend to rotate the axes even if it's not that beneficial. So I'm going to go ahead and draw the axes. So the y-axis will line up with the normal force, and the x-axis will line up with the frictional force. But remember, don't do it on that same diagram. Go down to part D, and you can just draw an xy axis, and then just draw the forces on this axis. So I'll leave the Fn where it is, and we'll leave the force of friction. The gravitational force, which was going downward, is broken into a y component, and this angle right here is the same as the angle of the ramp. That can be shown with geometry. We did a couple examples like that in class. So this one is going to be Fg cosine theta, and the second arrow going to the left is going to be the Fg sine of theta. And then the pushing force, that also means we can cross this one, the gravity, off the diagram, now that we've broken it into components. And the pushing force, which is horizontal, that's the Fp, that angle is the same as the angle of the ramp. So to break that one into components, we're going to have an Fp cosine theta going in that direction, and an Fp sine theta in the y direction. And now we can cross that one off. So another diagram looks kind of like a jumble right now, but just to make sure you've got everything, the only force in the positive y direction is Fn. In the negative y direction, we have an Fp sine of theta and an Fg cosine of theta. In the positive x direction, we just have an Fp cosine theta, and in the negative x direction, we have an Fr and also an Fg sine theta. So now we can get to the point where we start doing the sum of the forces in the x and y direction. So the sum of the forces in the x direction, since the sled is not accelerating, still moving at a constant speed, it's equal to 0, which means we can set the forces on the right, Fp cosine theta, equal to the two forces on the left. So Fp cosine theta equals FFR plus Fg sine of theta. Plug in all the formulas that we know. So there's no formula for the pushing force. We'll just leave that as Fp. Cosine theta is equal to the frictional force is mu k times Fn plus, and then the gravitational force is mg, and then sine of theta. That's as far as we can go so far in the x direction. So let's also focus on the y direction. The sum of the forces in the y direction is equal to 0, which means we can set the upward forces, the upward force, Fn, equal to the two downward forces. So Fn equals Fp sine of theta plus Fg cosine of theta. And plug in the formulas that we know here. The Fn doesn't have a formula, neither does the Fp. So Fp sine theta, the only one that does have a formula is the Fg, and that's just equal to m times g. So now we've got this equation on the right solved for the normal force, so we can take that and plug that in for the normal force right here. So this is going to go there, and that will leave us with a pretty long equation now. It is Fp cosine of theta equals mu k times the normal force, which is Fp sine theta, plus mg cosine of theta, and then after that just continue this equation, so we got the plus mg sine theta. So plus mg sine of theta, and let's go ahead and distribute that mu k into the parentheses. So Fp cosine theta equals mu k Fp sine of theta plus mu k mg cosine theta plus mg sine of theta. We're trying to solve for the pushing force, so I want to get all the terms with an Fp over on one side of the equation. So I'm just going to bring this term over to that side. So it's now Fp cosine theta minus mu k Fp sine of theta equals mu k mg cosine of theta plus mg sine of theta. And just like in part B, where we factored out the tension, we're going to just factor out the pushing force. So Fp times the cosine of theta minus mu k times the sine of theta is equal to, and on the other side of the equation, even though it's not critical to do so, since both these terms have an mg in it, I'm just going to go ahead and factor that out. So mg times mu k cosine of theta plus the sine of theta. And then the last step would be to get the Fp by itself, divide both sides by this whole term in parentheses. So the final answer, which I'll bring up here, is that Fp is equal to mg times mu k cosine theta plus sine of theta divided by cosine of theta minus mu k times the sine of theta.